CIET NCERT presents AudioBook Ganit Prakash, Textbook of Mathematics for Grade 8.
Chapter number 6, page number 136. We distribute, yet things multiply. On the right side of the page, we are provided with a QR code, scanning which we can reach out to the additional resources to this chapter. We have learnt how algebra makes use of letter symbols to write general statements about patterns and relations in a compact manner. Algebra can also be used to justify or prove claims and conjectures like the many properties you learnt in the previous chapter, and to solve problems of various kinds. Distributivity is a property relating multiplication and addition that is captured concisely using algebra. In this chapter, we explore different types of multiplication patterns and show how they can be described in the language of algebra by making use of distributivity. 6.1 Some properties of multiplication. Increments in products. Consider the multiplication of two numbers. Say 23 multiplied by 27. First question. By how much does the product increase if the first number 23 is increased by 1? Question number 2. What if the second number 27 is increased by 1? Question number 3. How about when both numbers are increased by 1? Do you notice a pattern that could help generalize our observations to the product of any two numbers? Let us first consider a simpler problem. Find the increase in the product when 27 is increased by 1. From the definition of multiplication and the commutative property, it is clear that the product increases by 23. This can be observed from the distributive property of multiplication as well. If A, B and C are three numbers, then A within brackets B plus C is equal to AB plus AC. Page number 137. This property can be visualized nicely using a diagram. In figure, we have dots in A number of rows and B number of columns as AB, and adjacent to this we have another figure in which we have dots arranged in A rows and C number of columns. So, the product is AC. This can be explained as A within brackets B plus C. This is called the distributive property of multiplication over addition. Using the identity A within brackets B plus C is equal to AB plus AC, with A is equal to 23, B is equal to 27 and C is equal to 1, we have 23 within brackets 27 plus 1 is equal to 23 into 27 plus 23. 23 is written inside a box with increase below it. Remember that here A within brackets B plus C and 23 within brackets 27 plus 1 mean A multiplied by within brackets B plus C and 23 multiplied by within brackets 27 plus 1 respectively. We usually skip writing the multiplication symbol before or after brackets, just as in the case of expressions like 5a, xy, etc. We can also similarly expand a plus b within brackets into c using the distributive property as follows. A plus b within brackets into c is equal to c into within brackets a plus b. That is commutativity of multiplication. That is equal to c into a plus c into b. Distributivity. That is equal to ac plus bc. Commutativity of multiplication. We can use the distributive property to find in general how much a product increases if one or both the numbers in the product are increased by 1. Suppose the initial two numbers are a and b. If one of the numbers, say b, is increased by 1, then we have a multiplied by b plus 1 is equal to ab into a. A is written inside the square with increase below it. Now let us notice what happens if both numbers in a product are increased by 1. If in a product AB both A and B are increased by 1, then we obtain A plus 1 within brackets multiplied by B plus 1 within brackets. Page number 138. How do we expand this? Let us consider A plus 1 within brackets as a single term. Then, by the distributive property, we have A plus 1 within brackets multiplied by B plus 1 within brackets is equal to A plus 1 within brackets into B plus A plus 1 within brackets into 1. Again, applying the distributive property, we obtain A plus 1 within brackets multiplied by B plus 1 within brackets is equal to A plus 1 within brackets multiplied by B plus A plus 1 within brackets multiplied by 1. That is equal to AB plus within brackets B plus A plus 1, which is written inside the rectangle with the increase below it. On the right side, this has been explained with the help of an example. If A is equal to 23 and B is equal to 27, we get 23 plus 1 within brackets into 27 plus 1 within brackets. That is equal to 23 plus 1 within brackets into 27 plus 23 plus 1 within brackets into 1. That is equal to 23 into 27 plus within brackets 27 plus 23 plus 1 within brackets, and this is written inside the rectangular box with increase below it. Thus, the product AB increases by A plus B plus 1 when each of A and B are increased by 1. Next question. What would we get if we had expanded A plus 1 within brackets multiplied by B plus 1 within brackets by first taking B plus 1 within brackets as a single term? Try it. Next question. What happens when one of the numbers in a product is increased by 1 and the other is decreased by 1? Will there be any change in the product? Let us again take the product A into B of two numbers A and B. If A is increased by 1 and B is decreased by 1, then their product will be A plus 1 within brackets multiplied by b minus 1 within brackets. Expanding this, we get a plus 1 within brackets multiplied by b minus 1 within brackets is equal to a plus 1 within brackets into b minus a plus 1 within brackets into 1. That is equal to a into b plus b minus a plus 1 within brackets. That is equal to a into b plus b minus a minus 1 within a rectangular box, and increase is written below it. On the right side, we are explained this with the help of an example. If a is equal to 23 and b is equal to 27, we get 23 plus 1 within brackets multiplied by 27 minus 1 within brackets, that is equal to 23 plus 1 within brackets into 27 minus 23 plus 1 within brackets into 1. That is equal to 23 multiplied by 27 plus 27 minus within brackets 23 plus 1. That is equal to 23 into 27 plus 27 minus 23 minus 1 is written inside the rectangular box with increase below it. Next question. Will the product always increase? Find 3 examples where the product decreases. Next question. What happens when a and b are negative integers? Check by substituting different values for a and b in each of the given cases. For example, a is equal to minus 5, b is equal to 8, or a is equal to minus 4, b is equal to minus 5, etc. We have learnt that integers also satisfy the distributive property. That is, if x, y and z are any 3 integers, then x into within brackets y plus z is equal to x into y plus x into z. Thus, the expressions we have for increase of products hold when the letter numbers take on negative integer values as well. Recall that 2 algebraic expressions are equal if they take on the same values when their letter numbers are replaced by numbers. Page number 139. These numbers could be any integers. Mathematical statements that express the quality of 2 algebraic expressions such as a multiplied by b plus 8 within brackets is equal to a into b plus 8 into a, or a plus 1 within brackets multiplied by b minus 1 within brackets is equal to a into b plus b minus a minus 1, etc. are called identities. Next question. By how much will the product of 2 numbers change if one of the numbers is increased by m and the other by n? If a and b are the initial numbers being multiplied, they become a plus m and b plus n. A plus m within brackets multiplied by b plus n within brackets is equal to a plus m within brackets into b plus a plus m within brackets into n. That is equal to a into b plus m into b plus a into n plus m into n. The increase is a into n plus b into m plus m into n. Notice that the product is the sum of the product of each term of a plus m within brackets with each term of b plus n within brackets. Identity 1. A plus m within brackets multiplied by b plus n within brackets is equal to a multiplied by b plus m multiplied by b plus a multiplied by n plus m multiplied by n. This identity can be visualized as follows. In the figure, we have dots arranged in a number of rows and b number of columns with their product as a into b. Beside this, we have dots arranged in a number of rows and n number of columns with the product an. Below AB product, we have another arrangement of dots where we can find m number of rows and b number of columns with their product as mb, and below an we have another arrangement of m rows and n columns with dots with the product m into n, thus explaining a plus m within brackets multiplied by b plus n within brackets. Page number 140. This identity can be used to find how products change when the numbers being multiplied are increased or decreased by any amount. Can you notice how this identity can be used when one or both numbers are decreased? For example, let us reconsider the case when one number is increased by 1 and the other decreased by 1. Let us write the product a plus 1 within brackets multiplied by b minus 1 within brackets as a plus 1 within brackets multiplied by b plus minus 1 within brackets. Taking m is equal to 1 and n is equal to minus 1 in identity 1, we have a into b plus 1 into b plus a into minus 1 within brackets plus 1 within brackets into minus 1 within brackets, that is equal to a into b plus b minus a minus 1, which is the same expression that we obtained earlier. Next question. Use identity 1 to find how the product changes when, first part, one number is decreased by 2 and the other increased by 3. Second part, both numbers are decreased, one by 3 and the other by 4. Next question. Verify the answers by finding the products without converting the subtractions to additions. Generalizing this, we can find the product a plus u within brackets multiplied by b minus v within brackets as follows. A plus u within brackets multiplied by b minus v within brackets is equal to a plus u within brackets multiplied by b minus a plus u within brackets multiplied by v, that is equal to a into b plus u into b minus within brackets a into v plus u into v, that is equal to a into b plus u into b minus a into v minus u into v. Check that this is the same as taking m is equal to u and n is equal to minus v in identity 1. As in identity 1, the product a plus u within brackets multiplied by b minus v within brackets is the sum of the product of each term of a plus u within brackets a and u with each term of b minus v within brackets b and minus v. Notice that the signs of the terms in the products can be determined using the usual rules of integer multiplication. Notice how the rules of integer multiplication allows us to handle multiple cases using a single identity. Next question, expand. First part, a minus u within brackets multiplied by b plus v within brackets. Second part, a minus u within brackets multiplied by b minus v within brackets. We get a minus u within brackets multiplied by b plus v within brackets is equal to a into b minus u into b plus a into v minus u into v, and a minus u within brackets multiplied by b minus v within brackets is equal to a into b minus u into b minus a into v plus u into v. The distributive property is not restricted to two terms within a bracket. Next question, example 1. Expand 3 into a upon 2 within brackets a minus b plus 1 upon 5. 3 into a upon 2 within brackets a minus b plus 1 upon 5 is equal to 3 into a upon 2 into a within brackets minus 3 into a upon 2 into b within brackets plus 3 into a upon 2 into 1 upon 5 within brackets. The terms can be simplified as follows. 3 into a upon 2 into a is equal to 3 upon 2 into within brackets a into a. Page number 141. Using exponent notation, we can write 3 upon 2 into within brackets a into a is equal to 3 upon 2 into a square. 3 into a upon 2 into b is equal to 3 upon 2 into within brackets a into b is equal to 3 upon 2 ab. 3 into a upon 2 into 1 upon 5 is equal to 3 upon 2 into 1 upon 5 within brackets multiplied by a is equal to 3 upon 10 multiplied by a. So, we get 3 into a upon 2 within brackets a minus b plus 1 upon 5 is equal to 3 upon 2 a square minus 3 upon 2 ab plus 3 upon 10 multiplied by a. Next question. Can any two terms be added to get a single term? For example, can 3 upon 2 a square and 3 upon 10 a be added to get a single term? We notice that no two terms have exactly the same letter numbers, which would have allowed them to be simplified into a single term. So, a further simplification of the expression is not possible. Recall that we call terms having the same letter numbers like terms. Example 2. Expand a plus b within brackets multiplied by a plus b within brackets. We have a plus b within brackets multiplied by a plus b within brackets is equal to a plus b within brackets multiplied by a plus b within brackets multiplied by b is equal to a multiplied by a plus b multiplied by a plus a into b plus b multiplied by b. That is equal to a square plus ba plus AB plus B square. Since BA is equal to AB, we have two terms having the same letter numbers AB or that are like terms and so can be added. BA plus AB is equal to AB plus AB, that is equal to 2AB. So we get A plus B within brackets multiplied by A plus B within brackets, that is equal to A square plus 2AB plus B square. Example 3. Expand A plus B within brackets multiplied by A square plus 2AB plus B square within brackets. A plus B within bracket multiplied by A square plus 2AB plus B square within brackets is equal to A plus B within brackets into A square plus A plus B within brackets into 2AB plus A plus B within brackets multiplied by B square is equal to A into A square within brackets plus BA square plus A into 2AB within brackets plus B into 2AB within brackets plus AB square plus B into B square within brackets. The terms can be simplified as follows. A multiplied by A square is equal to A cube. Y within brackets. AB square is equal to A square B. A into 2AB is equal to 2 into A into B, that is equal to 2A square B. B into 2AB is equal to 2 into A into B, that is equal to 2AB square. B into B square is equal to B cube. So, A plus B within brackets multiplied by A square plus 2AB plus B square within brackets is equal to A cube plus A square B plus 2A square B plus 2AB square plus AB square plus B cube. We notice that A square B and 2A square B have the same letter numbers within brackets or comma are like terms, close the bracket, and so can be added. Page number 142. A square B plus 2A square B is equal to 1 plus 2 within brackets into A square B, that is equal to 3A square B. Similarly, AB square and 2AB square are like terms and so can be added. AB square plus 2AB square is equal to 1 plus 2 within brackets into AB square is equal to 3AB square. Thus we have A plus B within brackets into A square plus 2AB plus B square within brackets is equal to A cube plus 3A square B plus 3AB square plus B cube. A pinch of history. The distributive property of multiplication over addition was implicit in the calculations of mathematicians in many ancient civilizations, particularly in ancient Egypt, Mesopotamia, Greece, China, and India. For example, the mathematicians Euclid in geometric form and Aryabhatta in algebraic form use the distributive law in an implicit manner extensively in their mathematical and scientific works. The first explicit statement of the distributive property was given by Brahmagupta in his work Brahmasputa Siddhanta, verse 12.55 within brackets, who referred to the use of the property for multiplication as khanda gunan, multiplication by parts. His verse states the multiplier is broken up into two or more parts whose sum is equal to it. The multiplicand is then multiplied by each of these and the results added. That is, if there are two parts, then using letter symbols, this is equivalent to the identity a plus b within brackets into c is equal to a into c plus b into c. In the next verse, within brackets verse 12.56, Brahmagupta further describes a method for doing fast multiplication using this distributive property, which we explore further in the next section. Figure it out. Question number 1. Observe the multiplication grid given here. Each number inside the grid is formed by multiplying two numbers. If the middle number of a 3 by 3 frame is given by the expression P into Q, as given in the figure, write the expressions for the other numbers in the grid. Here we are provided a number grid in 10 rows and 10 columns, and we get the products as 1 multiplied by 1 is 1, 1 multiplied by 2 is 2 in the first row, 1 multiplied by 3 is 3, 1 multiplied by 4 is 4, and 1 into 5 is 5, 1 multiplied by 6 is 6, 1 multiplied by 7 is 7, 1 multiplied by 8 is 8, 1 multiplied by 9 is 9, and 1 multiplied by 10 is 10. Likewise, for the second row, 2 multiplied by 1 is 2, 2 multiplied by 2 is 4, 2 multiplied by 3 is 6, 2 multiplied by 4 is 8, 2 multiplied by 5 is 10, 2 multiplied by 6 is 12, 2 multiplied by 7 is 14, 2 multiplied by 8 is 16, 2 multiplied by 9 is 18, and 2 multiplied by 10 is 20. In the third row, we have 3 multiplied by 1 is 3, 3 multiplied by 2 is 6, 3 multiplied by 3 is 9, 3 multiplied by 4 is 12, 3 multiplied by 5 is 15, 3 multiplied by 6 is 18, 3 multiplied by 7 is 21, 3 multiplied by 8 is 24, 3 multiplied by 9 is 27, 3 multiplied by 10 is 30. In the fourth row, likewise 4 multiplied by 1 is 4, 4 multiplied by 2 is 8, 4 multiplied by 3 is 12, 4 multiplied by 4 is 16, 4 multiplied by 5 is 20, 4 multiplied by 6 is 24, 4 multiplied by 7 is 28, 4 multiplied by 8 is 32, 4 multiplied by 9 is 36, 4 multiplied by 10 is 40. 5 multiplied by 1 is 5, 5 multiplied by 2 is 10, 5 multiplied by 3 is 15, 5 multiplied by 4 is 20, 5 multiplied by 5 is 25, 5 multiplied by 6 is 30, 5 multiplied by 7 is 35, 5 multiplied by 8 is 40, 5 multiplied by 9 is 45, 5 multiplied by 10 is 50. Likewise, 6 multiplied by 1 is 6, 6 multiplied by 2 is 12, 6 multiplied by 3 is 18, 6 multiplied by 4 is 24, 6 multiplied by 5 is 30, 6 multiplied by 6 is 36, 6 multiplied by 7 is 42, 6 multiplied by 8 is 48, 6 multiplied by 9 is 54, 6 multiplied by 10 is 60. 7 multiplied by 1 is 7, 7 multiplied by 2 is 14, 7 multiplied by 3 is 21, 7 multiplied by 4 is 28, 7 multiplied by 5 is 35, 7 multiplied by 6 is 42, 7 multiplied by 7 is 49, 7 multiplied by 8 is 56, 7 multiplied by 9 is 63, and 7 multiplied by 10 is 70. For the 8th row, 8 multiplied by 1 is 8, 8 multiplied by 2 is 16, 8 multiplied by 3 is 24, 8 multiplied by 4 is 32, 8 multiplied by 5 is 40, 8 multiplied by 6 is 48, 8 multiplied by 7 is 56, 8 multiplied by 8 is 64, 8 multiplied by 9 is 72, 8 multiplied by 10 is 80. For the 9th row, 9 multiplied by 1 is 9. 9 multiplied by 2 is 18. 9 multiplied by 3 is 27. 9 multiplied by 4 is 36. 9 multiplied by 5 is 45. 9 multiplied by 6 is 54. 9 multiplied by 7 is 63. 9 multiplied by 8 is 72. 9 multiplied by 9 is 81. 9 multiplied by 10 is 90. And in the last row we have 10 multiplied by 1 is 10. 10 multiplied by 2 is 20. 10 multiplied by 3 is 30. 10 multiplied by 4 is 40. 10 multiplied by 5 is 50. 10 multiplied by 6 is 60. 10 multiplied by 7 is 70. 10 multiplied by 8 is 80. 10 multiplied by 9 is 90. And 10 multiplied by 10 is 100. On the right side, we have 3 by 3 frame which has been highlighted, and it has numbers 15, 18, 21 in the first row, 20, 24, 28 in the second row, and 25, 30 and 35 in the third row, which have been explained as 15 as 3 into 5, 18 as 3 into 6, 21 as 3 into 7. Likewise, in the second row we have 20 as 4 into 5, 24 as 4 into 6, 28 as 4 into 7. And in the third row, we have 25 as 5 into 5 and 30 as 5 into 6, 35 as 5 into 7. There is a blank 3 by 3 grid with the innermost number written with the value PQ. Page number 143. Question number 2. Expand the following products. First one, 3 plus u within brackets multiplied by v minus 3 within brackets. Second one, 2 upon 3 within brackets 15 plus 6a. Third one, 10a plus b within brackets multiplied by 10c plus d within brackets. Fourth one, 3 minus x within brackets multiplied by x minus 6 within brackets. Fifth one, minus 5a plus b within brackets multiplied by c plus d within brackets. Sixth one, 5 plus z within brackets multiplied by y plus 9 within brackets. Next question, find 3 examples where the product of two numbers remains unchanged when one of them is increased by 2 and the other is decreased by 4. Next question, expand first one. A plus ab minus 3b square within brackets multiplied by 4 plus b. And second one, 4y plus 7 within brackets multiplied by y plus 11z minus 3. Question number 5. Expand first one. A minus b within brackets multiplied by a plus b within brackets. Second one, a minus b within brackets multiplied by a square plus ab plus b square within brackets. And third one, a minus b within brackets multiplied by a cube plus a square b plus ab square plus b cube within brackets. Do you notice any pattern? What would be the next identity in the pattern that you notice? Can you check it by expanding? Fast multiplications using the distributive property. The distributive property can be used to come up with the quick methods of multiplication when certain types of numbers are multiplied. When one of the numbers is 11, 101, 1001 and so on. Next question. Use the following multiplications to find the product of a number with 11 in the single step. A. 3874 multiplied by 11. Let us take the first multiplication. 3874 into 11 is equal to 3874 multiplied by within brackets 10 plus 1, that is equal to 38,740 plus 3,874. So, we can add 38,740 plus 3,874. There is a blank space provided. You are expected to fill that. Part B is 5,678 multiplied by 11. Notice how the digits are getting added. Let us take a 4-digit number DCBA. That is the number that has D in the thousandth place, C in the hundreds place, B in the tens place, and A in the units place. DCBA multiplied by 10 plus 1 within brackets is equal to DCBA into 10 plus DCBA. This becomes DCBA0, and we write A below 0, B below A, C below B, and D below C, and we add. We get D below D, and C plus D is written below C and D. B plus C is written below B and C. A plus B is written below A plus B, and 0 plus A on adding gives us A, which is written below A. Page number 144. This can be used to obtain the product in one line. Step 1. 3,874 into 11. When we multiply by 4, we get 4. In the step 2, 3,874 multiplied by 11, we get 14 by taking 1 carryover. In step 3, 3,874 when multiplied by 11 gives us 614 by taking carryover. In step 4, we have 3,874 multiplied by 11 as 2,614. The process has been explained in the form of steps. In the step 5, we have 3,874 into 11 as 42,614. Next question. Describe a general rule to multiply a number within brackets of any number of digits by 11 and write the product in one line. Evaluate first part 94 into 11, second part 495 into 11, third part 3,279 into 11, fourth part 4791256 multiplied by 11. Next question. Can we come up with a similar rule for multiplying a number by 101? Next question. Multiply 3,874 by 101. Let us take a 4-digit number DCBA. DCBA multiplied by 101 is equal to DCBA into within brackets 100 plus 1, that is equal to DCBA into 100 plus DCBA. This becomes DCBA 00, and we write DCBA below BA 00. On adding, we get D below D and C below C. On adding B and D, we get B plus D. On adding A and C, we get A plus C. On adding B plus 0, we get B. On adding A plus 0, we get A. Next question. Use this to multiply 3874 into 101 in one line. Next question. What could be the general rule to multiply a number by 101 and write the product in one line? Extend this rule for multiplication by 1001, 10,001. Next question. Use this to find first part 89 into 101, second part 949 into 101, third one 265831 multiplied by 1001, fourth one 1111 multiplied by 1001, fifth one 9734 multiplied by 99, and sixth one 23,478 multiplied by 999. Such methods of applying the distributive property to easily multiply two numbers were discussed extensively in the ancient mathematical works of Brahmagupta within brackets 628 CE, Sridharacharya within brackets 750 CE, and Bhaskaracharya within brackets Leelavati 1150 CE. In his work Brahmasputa Siddhanta within brackets verse 12.56, Brahmagupta refers to such methods for fast multiplication using the distributive property as Istagunan. Page number 145. 6.2 Special cases of the distributive property. Square of the sum oblique difference of two numbers. Question. The area of a square of side length 60 units is 3600 square units within brackets 60 square, and that of a square of side length 5 units is 25 square units within brackets 5 square. Can we use this to find the area of a square of side length 65 units? A square of side length 65 can be split into 4 regions as given here in the figure. A square of side length 60, a square of side length 5, and 2 rectangles of side length 60 and 5. The area of the square of side length 65 is the sum of the areas of all its constituent parts. Can you find the areas of the 4 parts in the figure given here? We get 65 square is equal to 60 plus 5 within brackets square is equal to 60 square plus 5 square plus 2 into within brackets 60 into 5. That is equal to 3600 plus 25 plus 600 is equal to 4225 square units. Let us multiply 60 plus 5 within brackets into 60 plus 5 within brackets using the distributive property. 60 plus 5 within brackets into 60 plus 5 within brackets is equal to 60 into 60 plus 5 into 60 plus 60 into 5 plus 5 into 5. That is equal to 60 square plus 2 into within bracket 60 into 5 plus 5 square. Beside this, we are provided with a picture in which we have a square having side length 65. It is represented as 60 and 5. So total side length is 65. Likewise, we have on the other side length also 60 and plus 5 gives us 65. And there's a dotted line which is separating this, as you have 60 square in the middle and 60 into 5 rectangle besides, and 60 into 5 a rectangle below it, and 5 square, 1 square in the right corner. Next question. What if we write 65 square as 30 plus 35 within brackets square, or 52 plus 13 whole square? Draw the figures and check the area that you get. Let us examine the general expression for the square of sum of two numbers, a plus b whole square. Using the distributive property, a plus b whole square can be expanded as a plus b within brackets into a plus b within brackets is equal to a into a plus a into b plus b into a plus b into b, that is equal to a square plus 2ab plus b square, as we had already learnt in example 2. Identity 1a, a plus b whole square is equal to a square plus 2ab plus b square. The explanation of this identity has pictorially been explained with the help of a diagram. In this, we have a square of side length a plus b, and which has been represented inside the square as a square, b square, a into b and b into a. Next question. If a and b are any two integers, is a plus b whole square always greater than a square plus b square? If not, when is it greater? Next question. Use identity 1a to find the values of 104 square, 37 square. Hint provided is decompose 104 and 37 into sums or differences of numbers whose squares are easy to compute. Page number 146. Next question. Use identity 1a to write the expressions for the following. First part, m plus 3 whole square. Second one, 6 plus p whole square. Next question, expand 6x plus 5 whole square. Here we are provided with a box which has two columns. In the first column, using the distributive property, we have 6x plus 5 whole square, which is explained as 6x plus 5 whole square is equal to 6x plus 5 within brackets multiplied by 6x plus 5, that is equal to 6x into 6x within brackets plus 5 into 6x within brackets plus 6x into 5 within brackets plus 5 into 5, that is equal to 6x whole square plus 2 into within brackets 6x into 5 plus 5 square, that is equal to 36x square plus 60x plus 25. Beside this, we have been explained the expansion of this identity 6x plus 5 whole square. Using the identity, we have 6x whole square plus 5 square plus 2 into within brackets 6x into 5, that is equal to 36x square plus 25 plus 60x. If you have difficulty remembering or using the general rule, you can just apply the distributive property to multiply and get the desired result. Next question. Expand 3j plus 2k whole square using both the identity and by applying the distributive property. Next question. Can we use 60 square that is 3600 within brackets, and 5 square, that is equal to 25 within brackets, to find the value of 60 minus 5 whole square or 55 square. Let us approach this through geometry by drawing a square of side length 55 sitting inside a square of side length 60. Area of a square of side length 55 is 60 minus 5 whole square is equal to 55 square. We can get the area of the square of side length 55 by taking the area of the square of side length 60 and removing the areas of the two rectangles of side length 60 and 5. That is 60 square minus 60 into 5 within brackets minus 5 into 60 within brackets. By doing this, we remove the area of the small square of side length 5 twice. What can we do with this expression to get the actual area? We can add back the area of the square of side length 5 to this expression. That way, we are only subtracting this area once. The same has been explained with the help of a figure on the left side of the page, in which we have the side length of a square as 55 and we have beside a rectangle of side length 5 and we have the side length of the square as 60 outside the square of side length 55. We can clearly observe the measurements as 60 into 60 and minus 5 into 60 and 5 into 5 and minus 60 into 5, which is explained in this diagram with the help of two colors, blue and red. Page number 147. So, 60 minus 5 whole square is equal to 60 square minus 60 into 5 within brackets minus 5 into 60 within brackets plus 5 square. That is equal to 3600 minus 300 minus 300 plus 25. That is equal to 3025. The area of the square of side length 55 is 3025 square units. We have learnt what a plus b whole square gives when expanded. What is the expansion of a minus b whole square? Using the distributive property, a minus b whole square is equal to a minus b within brackets into a minus b within brackets. That is equal to a square minus ba minus ab plus b square. That is equal to a square minus 2ab plus b square. Next question. We can also use the expansion of a plus b whole square to find the expansion of a minus b whole square. Think how? Hint provided is a minus b whole square is equal to a plus within brackets minus b whole square. We can now directly use the expansion of a plus b whole square. A plus minus b within brackets whole square is equal to a square plus minus b whole square plus 2 into a into minus b. Identity 1b. A minus b whole square is equal to a square plus b square minus 2ab. Next question. Find the general expansion of a minus b whole square using geometry as we did for 55 square. Next question. Use the identity a minus b whole square to find the values of a 99 square and b 58 square. Next question. Expand the following using both identity 1b and by applying the distributive property. First one, b minus 6 whole square. Second one, minus 2a plus 3 whole square. Third one, 7y minus 3 upon 4z whole square. Investigating patterns. Pattern 1. Observe the following pattern. 2 within brackets 2 square plus 1 square is equal to 3 square plus 1 square. 2 within brackets 3 square plus 1 square is equal to 4 square plus 2 square. 2 within brackets 6 square plus 5 square is equal to 11 square plus 1 square. 2 within brackets 5 square plus 3 square is equal to 8 square plus 2 square. Page number 148. Take a pair of natural numbers. Calculate the sum of their squares. Can you write twice this sum as a sum of 2 squares? Try this with other pairs of numbers. Have you figured out a pattern? Notice that 2 within brackets 5 square plus 6 square is equal to 6 plus 5 whole square plus 6 minus 5 whole square. Next question. Do the identities given here help in explaining the observed pattern? A plus b whole square is equal to a square plus 2ab plus b square. A minus b whole square is equal to a square minus 2ab plus b square. A plus b whole square plus a minus b whole square is equal to a square plus 2ab plus b square within brackets plus a square minus 2ab plus b square within brackets. Adding the like terms, a square plus a square is equal to 2a square, b square plus b square is equal to 2b square, and 2ab minus 2ab is equal to 0. We get 2 within brackets a square plus b square is equal to a plus b whole square plus a minus b whole square. Pattern 2. Next question. Here is a related pattern. Try to describe the pattern using algebra to determine if the pattern always holds. 9 into 9 minus 1 into 1 is equal to 10 into 8. 8 into 8 minus 6 into 6 is equal to 14 into 2. 7 into 7 minus 2 into 2 is equal to 9 into 5. 10 into 10 minus 4 into 4 is equal to 14 into 6. The pattern here appears to be a square minus b square is equal to a plus b within brackets into a minus b within brackets. Is this a true identity? Using the distributive property, we get a plus b within brackets into a minus b within brackets is equal to a square minus ab plus ba minus a square. Adding the like terms, ab plus within brackets minus ab is equal to 0. We notice that indeed identity 1c, a plus b within brackets into a minus b within brackets is equal to a square minus b square. You had learnt this property earlier in Figure It Out, 5th first part. Next question. Use identity 1c to calculate 98 into 102 and 45 into 55. Next question. Show that a plus b within brackets into a minus b within brackets is equal to a square minus b square geometrically. Page number 149. The hint is provided here with the help of a picture in which we find a square which is purple in color whose side length is A, and we have a rectangle beside this with side length A and B. There is also a dotted line represented in order to show the movement of this red rectangle below the purple square. What do we get when this piece is moved is written beside this. Sridharacharya within bracket 750 CE gave an interesting method to quickly compute the squares of numbers using identity 1C. Consider the following modified form of this identity. A square is equal to A plus B within brackets, A minus B within brackets plus B square. Next question, why is this identity true? Now, for example, 31 square can be found by taking A is equal to 31 and B is equal to 1. 31 square is equal to 31 plus 1 within brackets, 31 minus 1 within brackets plus 1 square. That is equal to 32 into 30 plus 1. That is equal to 961. 197 square can be found by taking A is equal to 197 and B is equal to 3. 197 square is equal to 197 plus 3 within brackets, 197 minus 3 within brackets plus 3 square. That is equal to 200 into 194 plus 9. That gives us 38,809. Figure it out. Question number 1. Which is greater, A minus B whole square or B minus A whole square? Justify your answer. Question number 2. Express 100 as the difference of two squares. Question number 3. Find 406 square, 72 square, 145 square, 1097 square and 124 square using the identities you have learned so far. Question number 4. Do patterns 1 and 2 hold only for counting numbers? Do they hold for negative integers as well? What about fractions? Justify your answer. Page number 150. 6.3. Mind the mistake, mend the mistake. We have expanded and simplified some algebraic expressions given here to their simplest forms. First one, check each of the simplifications and notice if there is a mistake. Second one, if there is a mistake, try to explain what could have gone wrong. Third one, then write the correct expression. First one, minus 3p within brackets minus 5p plus 2q is equal to minus 3p plus 5p minus 2q, that is equal to p minus 2q. This is written in the first box. In the second box, we have 2 within brackets x minus 1 plus 3 into within brackets x plus 4. That is equal to 2x minus 1 plus 3x plus 4. That is equal to 5x plus 3. In the third box, we have y plus 2 within brackets y plus 2. That is equal to y plus 2 whole square. That is equal to y square plus 4y plus 4. In the fourth box, we have 5m plus 6n whole square is equal to 25m square plus 36n square. In the fifth box, we have minus q plus 2 whole square is equal to q square minus 4q plus 4. In the sixth box, we have 3a within brackets 2b into 3c is equal to 6ab into 9ac, that is equal to 54 a square bc. In the seventh one, we have 1 upon 2 within brackets 10s minus 6 plus 3, that is equal to 5s minus 3 plus 3, that is equal to 5s. In the eighth box, we have 5w square plus 6w, that is equal to 11w square. In the ninth box, we have 2a cube plus 3a cube plus 6a square b plus 6ab square is equal to 5a cube plus 12a square b square. In the 10th box, we have x plus 2 within brackets multiplied by x plus 5 within brackets is equal to x plus 2 within brackets into x plus x plus 2 within brackets into 5, that is equal to x square plus 2x plus 5x plus 10, that is equal to x square plus 7x plus 10. In the 11th box, we have a plus 2 within brackets multiplied by b plus 4, that is equal to ab plus 8. In the 12th box, we have ab square plus a square b plus a square b square, that is equal to ab within brackets a plus b plus ab. 6.4 This way or that way. All ways lead to the bay. Observe the pattern in the figure given here. Draw the next figure in the sequence. How many circles does it have? How many total circles are there in step 10? Write an expression for the number of circles in step K. In the first one, we are given 3 circles which have been arranged in a triangular form. In the second one, we have 6 circles in 2 rows and 2 circles below the 2 rows. In the third one, we have 4 circles in 3 rows and 3 circles below the first 3 columns. That means we have 3 circles in the first figure, 8 circles in the second figure and 15 circles in the third figure. There are many ways of interpreting this pattern. Here are some possibilities. Page number 151. Method 1. Step 1, we have 3 circles and for the fourth circle there is a dotted circle there representing 2 square minus 1, that is equal to 1 plus 1 whole square minus 1. In step 2, we have 3 by 3 box in which we have 8 circles and the 9th circle is given with a green dotted circle, that is 3 square minus 1, that is equal to 2 plus 1 whole square minus 1. In step 3, we have 15 circles and the 16th circle is visible with a green color and that can be written as 4 square minus 1, that is equal to 3 plus 1 whole square minus 1. In the next figure, in step 4, we can observe there are 24 circles and the 25th one can be observed with a green dotted structure. 5 square minus 1, that is equal to 4 plus 1 whole square minus 1 and so on For the step k, we can write it as k plus 1 whole square minus 1. Method 2. In step 1, we have one circle in a square and other two circles outside the square, which can be expressed as 1 plus 2 into 1. That is equal to 1 square plus 2 into 1. In step 2, we have 4 circles placed in a square box and 4 circles outside the square box, which can be expressed as 2 square plus 2 into 2. That is equal to 2 square plus 2 into 2. In the third step, we have 9 circles inside the square box and 6 circles outside the square box, which can be expressed as 3 square plus 2 into 3. That is equal to 3 square plus 2 into 3. In step 4, we have 16 circles inside the square box and 8 circles outside the square box, which can be expressed as 4 square plus 2 into 4. That is equal to 4 square plus 2 into 4, which can be expressed for step k as k square plus 2 into k. Method 3. In step 1, we can have 2 circles in one rectangular pattern and 1 circle outside it, which can be expressed as 1 into 2 plus 1. That is equal to 1 into 1 plus 1 within brackets plus 1. In step 2, we have 6 circles inside the rectangle and 2 circles outside the rectangle, which can be expressed as 2 into 3 plus 2, which can be still further expressed as 2 into 2 plus 1 within brackets plus 2. In step 3, we have 12 circles inside the rectangular box and 3 circles outside the rectangular box, which can be expressed as 3 into 4 plus 3. That is equal to 3 into within brackets 3 plus 1 plus 3. In step 4, we have 20 circles inside the rectangular box and 4 circles outside the rectangular box, which can be expressed as 4 into 5 plus 1. That is equal to 4 into within brackets 4 plus 1 plus 4. For step k, we can express this as k into within brackets k plus 1 plus k. Page number 152. Method 4. In step 1, we have 3 circles in squared boxes and we can express this as 1 into 3 is equal to 1 into 1 plus 2. In step 2, we have 2 circles in each box and we can find 4 such rectangular boxes. 2 into 4 is equal to 2 into within brackets 2 plus 2. In step 3, we have circles arranged in the form of triplets. We have 3, 3, 3, 3, 5 times. So 3 into 5 is equal to 3 into 3 plus 2 within brackets. In step 4, we have these circles arranged in a group of 4s. So we can write this as 4 into 6, that is equal to 4 into within brackets 4 plus 2. In step k, we can write down this as k into within brackets k plus 2. Does your method match any of these or is it different? Each expression that we have identified appears different. But are they really different? Since they describe the same pattern, they should all be the same. Let us simplify each expression and find out. We have 4 different expressions simplified here. First one says k plus 1 whole square minus 1. That is equal to k square plus 1 plus 2k minus 1. That is equal to k square plus 2k. For the second one, we have k square plus 2 into k. That is equal to k square plus 2k. For the third one, we have k into within brackets k plus 1 plus k. That is equal to k square plus k plus k. That is equal to k square plus 2k. And in the fourth expression, we have k into within brackets k plus 2. That is equal to k square plus 2k. When carried out correctly, all methods lead to the same answer, k square plus 2k. The expression k square plus 2k gives the number of circles at step k of this pattern. In mathematics, there are often multiple ways of looking at a pattern and different ways of approaching and solving the same problem. Finding such ways often requires a great deal of creativity and imagination. While one or two of the ways might be your favorite or favorites, it can be amusing and enriching to explore other ways as well. Next question. Use this formula to find the number of circles in step 15. Next question. Consider the pattern made of square tiles in the given picture. In the first one, we have 8 square tiles arranged with a blank space at the center. In the second picture, we have 12 tiles arranged with space for 4 tiles which is vacant at the center. In the third picture, we have 16 tiles arranged with blank space for 9 tiles. Page number 153. Next question. How many square tiles are there in each figure? Next question. How many are there in step 4 of the sequence? What about step 10? Next question. Write an algebraic expression for the number of tiles in step n. Share your methods with the class. Can you find more than one method to arrive at the answer? Next question. Find the area of the interior shaded region in the figure given here. All 4 rectangles have the same dimensions. Tadang's method. The total region is a square of side m plus n with an area m plus n whole square. Subtracting the area of 4 rectangles from the total area will give the area of the interior shaded region. That is m plus n whole square minus 4 into m into n. We have a picture of the same given here in which we can find the border and the color pink color and the shaded region inside this with brown color, and the border has width of m and the length is n. Yusuf's method. The shaded region is a square with side length n minus m within brackets. So, its area is n minus m whole square. Next question. By expanding both expressions, check that m plus n whole square minus 4 m into n is equal to n minus m whole square. Next question. Find out the area of the region with slanting lines in the figure. All 3 rectangles have the same dimensions in figure 1. We have 3 rectangles arranged in the shape of I and the rest region is shaded with slant lines. Anusha's method. Required area is equal to area ABCD minus area EFGH. Area of ABCD is equal to x square. Area of EFGH is equal to xy. So required area is equal to x square minus xy. This has been explained with the help of a picture given here. Vaishnavi's method. QS is equal to y plus x plus y. That is equal to x plus 2y. Area of PQSR is equal to x multiplied by x plus 2y within brackets. Required area is equal to area of PQSR minus area of the three rectangles. That is equal to x multiplied by x plus 2y within brackets minus 3xy. This also has been represented with the help of a picture here. Page number 154. Aditya's method. The required area is 2 times the area of JKLM. JK is equal to x minus y upon 2. KM is equal to x. Area JKML is equal to x within brackets x minus y upon 2. Required area is equal to 2 into area of JKML. That is equal to 2 into within brackets x minus y upon 2. That is equal to x within brackets x minus y. The same has been represented with the help of a figure here. Next question. By expanding the expressions, verify that all three expressions are equivalent. If x is equal to 8 and y is equal to 3, find the area of the shaded region. Next question. Write an expression for the area of the dashed region in the figure given here. Use more than one method to arrive at the answer. Substitute P is equal to 6, R is equal to 3.5, S is equal to 9 and calculate the area. Here we are given the measurements in the form of a picture in which you can find P, S, R which have been represented, and there is a dashed region as well. Figure it out. Question number 1. Compute these products using the suggested identity. First one, 46 square using identity 1a for a plus b whole square. Second one, 397 into 403 using identity 1c for a plus b into a minus b. Third one, 91 square using identity 1b for a minus b whole square. Fourth one, 43 into 45 using identity 1c for a plus b within brackets into a minus b. Question number 2. Use either a suitable identity or the distributive property to find each of the following products. First one, p minus 1 within brackets multiplied by p plus 11. Second one, 3a minus 9b within brackets multiplied by 3a plus 9b. Third one, minus within brackets 2y plus 5 within brackets 3y plus 4. Fourth one, 6x plus 5y whole square. Fifth one, 2x minus 1 upon 2 whole square. Sixth one, 7p multiplied by 3r multiplied by p plus 2 within brackets. Page number 155. Question number 3. For each statement, identify the appropriate algebraic expressions. First one, 2 more than a square number. 2 plus s plus 2 whole square, s square plus 2, s square plus 4, 2s square, 2 square s. Second one, 2s square, 2 square s. Second one, the sum of the squares of two consecutive numbers, m square plus n square, m plus n whole square, m square plus 1, m square plus m plus 1 whole square, m square plus m minus 1 whole square, m plus 1 within brackets whole square, 2m whole square plus 2m plus 1 whole square. Question number 4. Consider any 2 by 2 square of numbers in a calendar as given in the figure here. We have the month of February with the days and dates mentioned, in which 4, 5, 11 and 12 dates have been highlighted. Find products of numbers lying along each diagonal. That is 4 into 12 is equal to 48. 5 into 11 is equal to 55. Do this for the other 2 by 2 squares. What do you observe about the diagonal products? Explain why this happened. The hint provided is label the numbers in each 2 by 2 square as. We have a rectangular box here with 4 parts. One has A, other beside has A plus 1 within brackets, and below A we have expression A plus 7, and in the fourth box we have A plus 8. Question number 5. Verify which of the following statements are true. First one, k plus 1 within brackets, k plus 2 within brackets minus k plus 3 within brackets is always 2. Second one, 2q plus 1 within brackets, 2q minus 3 within brackets is a multiple of 4. Third one, squares of even numbers are multiples of 4 and squares of odd numbers are 1 more than multiples of 8. Fourth one, 6n plus 2 whole square minus 4n plus 3 whole square is 5 less than a square number. Question number 6. A number leaves a remainder of 3 when divided by 7 and another number leaves a remainder of 5 when divided by 7. What is the remainder when their sum, comma difference and product are divided by 7? Question number 7. Choose 3 consecutive numbers, square the middle one and subtract the product of the other 2. Repeat the same with other set of numbers. Page number 156. What pattern do you notice? How do we write this as an algebraic equation? Expand both sides of the equation to check that it is a true identity. Question number 8. What is the algebraic expression describing the following steps? Add any two numbers. Multiply this by half of the sum of the two numbers. Prove that this result will be half of the square of the sum of the two numbers. Question number 9. Which is larger? Find out without fully computing the product. First one, 14 into 26 or 16 into 24. Second one, 25 into 75 or 26 into 74. Question number 10. A tiny park is coming up in Dhauli. The plan is given in the picture. The two square plots, each of area g square square feet, will have a green cover. All the remaining area is a walking path w feet wide that needs to be tiled. write an expression for the area that needs to be tiled. Here we have a picture explaining the given measurements. We have two green areas which are square in shape in the middle, and rest area is tiled, which is yellow in color. Question number 11. For each pattern given here, first one, draw the next figure in the sequence. Second one, how many basic units are there in step 10? Third one, write an expression to describe the number of basic units in step Y. There is visual representation of the sequences which are expressed in yellow and blue color. For yellow, in step 1, there are 9 units. In the step 2, we have 16 units. In step 3, we have 27 such units to express the sequence. For the blue sequence, in step 1, we have 5 units. For step 2, we have 11 units used. For step 3, there are 19 such units used. Page number 157. Summary. First point, we extended the distributive property to find the product of two expressions, each of which has two terms. The general form for the same is a plus b within brackets into c plus d within brackets is equal to ac plus ad plus bc plus bd. Second point, we notice some special cases of this identity. A plus b whole square is equal to a square plus 2ab plus b square. A minus b whole square is equal to a square minus 2ab plus b square. In the third one, a plus b within brackets multiplied by a minus b within brackets is equal to a square minus b square. Third point, we considered different patterns and explored how to understand them using algebra. We also learned that often there are multiple ways to solve a problem and arrive at the same correct answer. Finding different methods to approach and solve the same problem is a creative process. Page number 158. It's puzzle time. Coin, conjoin. Arrange 10 coins in a triangle as given in the figure on the left. The task is to turn the triangle upside down by moving one coin at a time. How many moves are needed? What is the minimum number of moves? A triangle of 3 coins can be inverted, turned upside down within brackets with a single move, and a triangle of 6 coins can be inverted by moving 2 coins. The 10 coin triangle can be flipped with just 3 moves. Did you figure out how? Find out the minimum possible moves needed to flip the next bigger triangle having 15 coins. Try the same for bigger triangular numbers. Is there a simple way to calculate the minimum number of coin moves needed for any such triangular arrangement? Here we are provided with a picture in which we can find a triangular shape which has been formed with the help of 10 coins. Beside this, there is another picture of an inverted triangle formed by 10 coins. Below this page, here we can also find the picture of small kids wondering to solve the puzzle given here. Chapter 6 ends here.
Ganit Prakash, you were just listening to this audiobook, Textbook of Mathematics for Grade 8. Narration, Swarnlata Sharma. Sound recordist, Prasoon Kumar. Production assistant, Amarjit Sarkar. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.